Hello everyone, it's Maz Safo with you. Uh, I'm a mechanical engineer at Abdullah Gül University in Turkey, and I will be giving you a brief introduction about necking and consider its criterion. I specifically chose this topic because there is very limited information or research about it on YouTube for students to easily understand it, or even on Google. So I will just give a brief introduction about it. I hope it will be understandable for all of you. So let's first have a clear definition of what necking is. Necking is like the local deformation of a component, and it begins at the tensile point or the ultimate stress point of material. And after a certain maximum value of the load applied, the area of the middle portion of a specimen may begin to decrease because of the local instability, as can be seen here in the diagram on the right. And this phenomena is ultimately known as necking, and it is usually associated with the ductile material. The test specimen on the right experienced under a great load experiences necking, as we see, and the portion where necking occurs may be called the neck of the specimen, and eventually the neck becomes a fracture when enough strain is supplied. Also the figure on the left shows the necking region in a stress strain diagram for a ductile material. Now let's talk about necking in a more complicated way. Let's not say complicated or in a more engineering or material science way. The term necking is used to describe the localization or the localized reduction of the cross-sectional area of a specimen under a tensile load, as we already said. So necking occurs when an instability in the material causes its cross-section to decrease by a greater proportion than the strain hardens when undergoing tensile deformation. So let's say if the material begins to harden by a smaller portion than the decrease in the cross-sectional area, then the strain concentrates at the location of the highest stress or the lowest hardness. And we can also say that the greater the local strain, the greater the local decrease in cross-sectional area, which in turn causes even more concentration of strain, leading to a point of instability that causes the formation of a neck. And I will be explaining more about the instability point of necking in the upcoming slide. Now, the necking behavior is usually disregarded in the calculating of the calculation in engineering stress, but it is usually taken into account or consideration when determining true stresses and true strains. So let's now talk about the Consideri's criterion. Consideri is a scientist who published the basic criterion for necking in 1885. In his published article, he mentioned about 3 concepts were provided by him to understand the neck formation. The first concept was before deformation, all real materials have heterogeneities such as flows or local variations in dimensions or composition that cause local fluctuations in stresses and strains. And to determine the location of the incipient neck, these fluctuations need only be infinitesimal in magnitude. This concept determines the neck's location. But now we are considering or we are focusing more on the stability points that occurs by the necking. So these upcoming 2 points determine the stability of a material. During tensile deformation, the material decreases in cross-sectional area. And the third and the last one, during tensile deformation, the material strain hardens and the amount of hardening varies with the extent of deformation. Let's now understand the last 2 concepts in a more deeply way so that we have a clear understanding of the Consideri's criteria. I'll be explaining about how is the strain hardening rate related to the true stress strain curve. First, the instability point in the stress strain curve or in the material's mechanical behavior is explained by the considered criterion. Let's here examine that the blue line is the true stress strain curve and the orange line is the strain hardening rate. It is the strain hardening rate and the true stress strain curve here are represented by theta, which is the derivative of the stress with respect to strain. This criterion explains the plastic instability at the necking point by explaining and telling us that the material strengthens gradually as we plastically deform it, but at the necking point, the stress increases significantly, of course, due to the cross-sectional area decreasing at this specific point. The stress becomes greater than the hardening rate, which is how much the material strengthens of the material. And this balance between the strengthening of the material and the higher stress applied to the material creates the necking. Now let's have a clear understanding of how this equation was derived. First of all, let's consider this equation, which is the load carried, and sigma here is the true stress and A is the instantaneous area. And we can easily obtain it from the true stress strain curve, this equation I mean. Here at the necking point, the slope is 0, so df equals 0. And then by taking derivative from the right-hand side of the equation, it will also equal to 0. Then rearranging to get our first equation. So now here we have our first equation to use to derive the our equation for the criterion, considered criterion. Then we can write the true stress strain as the following, or the true strain as the following. It is a very relative with the change of the area because the area gets smaller. Then we can also rearrange our equation so that the two equations are now related to each other. Then rearranging again so that we finally get our equation for the considered criterion. The left-hand side of the equation represents the strain hardening rate and the right-hand side represents the true stress. At this point of necking, when stress reaches about the stress hardening rate, this is where instability occurs, and by this equations we proved our criterion. If, for example, at this point, as we can see here in the graph, sigma equals theta, then we observe necking. If the material was or has higher strain hardening rate, which means, for example, theta is greater than sigma, then it means that the two curves won't intersect with each other, and therefore the material will continue to elongate without necking, observing a homogeneous deformation. Of course, what I just explained is important to understand the plastic deformation capacity of the materials. Now that we had a clear understanding of the considered criterion and its equation, let's conclude what we said throughout our video. First of all, we discussed or had a clear understanding of what necking is in engineering or material science terms, and then we explained the considered criterion. We can easily say that, or we can easily conclude about the considered criterion that the hardening rate of the true stress is equal to the stress at the point at which the material can no longer support an increasing load. And beyond this point on the stress strain curve, the deformation will tend to localize in a neck. That's all for the video. Thanks a lot for your attention. I hope you got the knowledge you were looking for about considered criterion and necking. And if you have any question, feel free to drop your question in the comments. I will be glad to answer your questions. And you can also email me if you need anything else. Thanks a lot. see you in another video.